Hello, everyone. Welcome to the MathStat Prelim of August 2018, Problem 2. In this problem, we have a continuous time discrete state space Markov chain described by a generator matrix Q, and we're being asked a bunch of questions to apparently find a second-order expansion for the expectation of a certain integral. Now, at first glance, this problem seems really scary. It's notation intensive, but I don't think it's as bad as I think. I don't know what you think, but let's see what we can do. So first, a note about notation. If you've taken a class with me, I do use the notation x sub n for a discrete time Markov process, and I use x of t in parentheses for continuous time. And not everyone does that. I don't think anyone would ever use an n for a continuous time process, but people certainly do use a t for both discrete and continuous time. And so I like to switch to this parentheses notation to be really clear on that. In this problem, the author of the problem is using x sub t, which is fine, but it is a continuous time process. And I could go and change it all to this, but I see no reason to do that. Another thing in this problem is the reference to this x. X is the entire process, so it's the collection of random variables, xt, where t is greater than or equal to 0. So it's talking about the entire Markov process. Now, for a discrete state space continuous time process, we use a generator matrix to describe the process. You certainly don't want to or can't use a matrix of one-step transition probabilities because there is no such thing as one time step. So we call this Q, and it's filled with some Qij, and these are rates of transition from state I to state j. So in the problem, they give you some properties of Q, and they're really nothing new. So it says that Qij is greater than or equal to 0 for j not equal to I. Rates of transitions are always non-negative, except the diagonal terms. The diagonals of this matrix, those represent the rate of not changing from a state, the rate of staying where you are. And they are such that the rows sum to 0. So the rate of staying at state I, if you will, is the negative sum over all j not equal to I of Qij. So we're running across that ith row and summing everything else, taking its negative and putting it on the diagonal. And that shouldn't be new to anyone. Now, for a continuous time Markov process on a discrete state space, we have states changing, right? We jump from some state I to some state j. By jump, I mean move, because that could be up or down, and it could be more than one sort of increment at a time. And the times between the transitions are necessarily exponential. And the reason is that the exponential distribution is the only continuous time distribution with that lack of memory property. And that lack of memory property is needed in order to get the Markov property out of a process. You don't need to know this going into this problem because this stuff is spelled out in the problem. What do we want to look at? We're going to look at a certain random time that is called tau. This is the infimum over all t greater than or equal to 0, such that the process at time t is not equal to the process at time 0. So this is the first time the process transitions away from its original starting state. So given what we just talked about, this should have an exponential distribution. And it's given here as having an exponential distribution with rate equaling negative Qii. So note that that is positive because Qii is negative. And we're given that the probability that at this time, tau, we move to some state j, given that we started at some state I, is negative Qij over Qii. What is this saying? Imagine a simple birth and death, or maybe even more concrete, like an MM1Q, where you have arrivals with some constant rate lambda and service times with some rate mu. When you are at some point in time and you're at some state waiting for the next event to happen, the next event will happen at the minimum of 2 exponential times. You have to figure out if you're going to have a birth next or a death next. So if you have lambda as a birth rate and mu as a death rate, and I'm going to suppose, I'm just trying to give an example to make this notation seem a little more comfortable. I'm just going to assume that we are not at state 0 because things are just a little bit different down there because you can't die from 0. So when you're at a state I that's not 0, the time until the next birth is exponential with rate lambda, the time until the next death is exponential with rate mu, and the time until the next event is exponential with rate lambda plus mu. That's what you get when you take the minimum of those times. Now, if these are the only moves allowed and you know the time of the next event, how can you figure out which event it is? Is it a birth or is it a death? And if you were sort of simulating this process like this, where you just said event time, now is it a birth or death, you would have a birth with probability, so the proportion of the birth rate to the total rate, and a death with probability, the proportion of the death rate to the total rate. The Q matrix here, if you're at some state I, you can go up in this example, not this problem for the prelim, but in this example, you can go up to I plus 1, you can go down to I minus 1, or you can stay at I. And you'll go up to I plus 1 with rate lambda. You'll go down to I minus 1 with rate mu. The other rates out here are going to be zeros. And then the diagonal entry, the II entry, is going to be the negative of the sum of the rest of the rates in that row. So what are we seeing back up in this circle? Given we started the Markov chain and some state I, the time to the next event is the negative of the generator matrix entry on the diagonal. So in the example I was doing below, the QII was negative lambda plus mu. And so negative QII is lambda plus mu. That's the time until the next event. That's the rate for the exponential describing the time to the next event. And then this, it's easier to think about with this negative on the bottom. The probability, say you go from, in my MM1 example, I to I plus 1. So if J was I plus 1, then QI, I plus 1 is lambda, and the QI, I plus 1 over QII is lambda over lambda plus mu. The QII is negative, but we have a negative in the front. So I don't know if that took too much of your time, but I just wanted to point out that you know these things that are being given to you in this problem. Okay, so let's actually try to solve the problem. We're going to suppose that we're starting at time 0 in state I, and we have a function oh yes, by the way, this chain lives on the state space of integers 1, 2, up through capital N. It wasn't all that clear from the description. It's clear from the description because the generator matrix is capital N by capital N that it has that size. But we are using these integer values because we're going to take a function that takes values in 1, 2, up through N and gives you real numbers. And we're going to be plugging the process into that function. So the process had better be on this state space. So we're trying to find a second order expansion of a certain expectation of a certain integral. I don't actually think that's important right now. And I don't even think it's going to help with intuition to talk about it. So let's just go through the steps. It's leading us to a conclusion and just see if we can handle each step. In this problem, we are given an epsilon greater than 0, and we're given some events. The event A is that the state of X, so X is the entire process. I'm just going to say the process does not change in the time interval from 0 to epsilon. So after epsilon units of time, we're still where we started and we're always there. B is the event that the process changes exactly once in that amount of time. And C is the event that the process changes 2 or more times in that time interval. Part A. We want to use the given information about the exponential inter-event time and the Taylor series expansion for E to show that a probability has a certain form. So in part A, we're looking at the probability that the event A happens, and this is the probability that the process is unchanged in the time interval 0 to epsilon. So tau was the time of the first change. So this is the same thing as the probability that tau is actually greater than epsilon. Tau has an exponential distribution. This is just a tail probability for an exponential. Remember, the CDF for an exponential with rate lambda looks like this. Now we have negative QII in for lambda, and this is the CDF. We want the tail probability, and that's going to make this, not that you have to write 1 minus 1 minus, but it's going to make it 1 minus 1 minus e to the minus negative QII epsilon, which is e to the QII epsilon. Well, that's great. We found an expression for the given probability, but not the expression that we want. And here's where the expanding the E is going to come in. So you can write this, a Taylor series expansion around 0 or a Maclaurin series expansion, as 1 plus QII epsilon plus 1 over 2 factorial QII epsilon squared plus 1 over 3 factorial QII epsilon cubed, etc. In this problem, we want to cut this off with a little o of h term, or in this case, a little o of epsilon squared. So recall that a function f of h is little o of h if it's going to 0 as h goes to 0, and it's going fast enough to be able to outrun a denominator that's also going to 0. If something is little o of epsilon squared, then these h's are just going to be epsilon squareds. Going back to the expression we have here, what that's going to do is knock out the terms that have epsilon at cubed or higher. So for example, epsilon cubed is little o of epsilon squared, since if you look at epsilon cubed over epsilon squared, you get epsilon, which goes to 0 as epsilon goes to 0. So we end up keeping these terms, and then the rest of the terms get wrapped into a little o of epsilon squared. And so we are done with, well, part of this part A. So we have 1 plus QII epsilon plus 1/2 QII squared epsilon squared plus something that is little o of epsilon squared. We want to take this and we want to show something about an expectation here. So this is what we want to look at, and we want to show that it's equal to a given thing. which I think is going to kind of pop out naturally given what we have for the probability. Note that A is the event that the process has not changed in the time interval from 0 to epsilon. All of this, by the way, is predicated on us starting at state I. So I think really all of these should have, like, I'm not going to change it, but they should have maybe an I subscript, like on this expectation and on various probabilities. But given that the event A happened, I know that x of t is still I over the entire range of this integral. And that means that the integral is epsilon times f of I. And there's nothing random here. So this is epsilon times f of I times the probability of A occurring, which we have an expression for up here. When you multiply this out, you get epsilon times f of I plus qii epsilon squared times f of I. And then when you multiply this epsilon by, say, this term, you get an epsilon cubed. And as you go up, you get higher powers of epsilon, and epsilon cubed, epsilon to the fourth, etc. Those are all order little o of epsilon squared. And that's what we wanted to show. So we are done with part A. Okay, let's talk about part B. In part B, we want to find the conditional density, or PDF, of tau given that tau is less than or equal to epsilon. Remember, tau itself was exponential with rate equaling negative qii. So we've got an exponential distribution, but we're given that it is between 0 and epsilon. So what that does is cut off this part over here. And then what's left is not a valid PDF. It doesn't integrate to 1. So we need to make it integrate to 1. And to do that, we need to divide by the total area here. And this area is the probability that tau is less than or equal to epsilon. And that is the CDF for the exponential. So this is 1 minus e to the qii epsilon. And to finish this off, that's just that area. But the conditional PDF for tau, given that tau is less than or equal to epsilon, maybe I'll make this a function of t. This is just going to be the exponential e to the negative of the negative qii, so positive qii times t, over 1 minus e to the qii epsilon. And this is going to be for, or this is a great place to use an indicator, but this is going to be for t between 0 and epsilon. And it's going to be 0 otherwise. And we are done with part B. Okay, in part C, we want to compute what at first glance looks like a similar expectation times a probability, but I think it's going to be a little more complicated because before we conditioned on the event A happening, and A was the event that we had no change in our process between time 0 and time epsilon. And now we're conditioning on B, and B is the event that we had exactly 1 change. And that sounds like it's going to be a little more complicated. So let's see what we can do. We have a random variable tau, which is the first time the process changes. And the event A was the event that there was no change between 0 and epsilon. So that was equivalent to saying that the first change time is greater than epsilon. And I think it's going to be a good idea to define like a second tau, so we can talk about this first change time. So I'm going to let tau prime be the infimum over all t greater than or equal to tau. So how much further did we have to go after the process changed once? I want the smallest value for which xt is not the same thing as x tau, which is the value of the process at the very first change. So now we can say that the event B is the event that tau is less than or equal to epsilon, and epsilon is less than tau prime. This is how you get exactly one event occurring in the interval from 0 to epsilon. The time of the first event has to be less than or equal to epsilon, and the time of the second event has to be greater than epsilon. So now I can rewrite the thing we want to compute in terms of B in this new way. And in the prelim, we're given a pretty big hint here. We're given a hint that this is the same thing as the probability that tau is less than or equal to epsilon times a big conditional expectation. So why is this equal to the line above? I don't want to spend time on it right now. It's not part of the prelim. You're supposed to take this as given, but I will go back at the end of the video when we're done with the problem and show that equality. But how do we proceed from here, given that we have this equality? I need to compute this expectation, and there is a lot going on in here. There are 3 random variables or random quantities in this expectation. There's tau, the time of the first move away from state I. There's tau prime, the time of the first move away from wherever we moved to when we moved away from state I. And the process itself, I don't know the process, it's a random variable. So I do know this first probability because tau was exponential with rate negative qii, and that makes this 1 minus e to the positive qii epsilon, the CDF for that exponential. But I have way too much random stuff in here. So I am going to try to condition on 1 or 2 of these so that I get down to a computation involving only 1 random variable that hopefully is more tractable. I am going to condition on tau. You might say there's already a condition on tau over here, but what I want to do is nail down exactly what tau is. I only know that tau is less than or equal to epsilon, so I want to condition on tau being equal to some s. And because we're starting in the conditional land where tau is less than or equal to epsilon, I am not going to multiply when I do this conditioning on tau by the exponential negative qii distribution. I'm going to multiply by the distribution we found in part B, which is the conditional distribution. So let's go. I have 1 minus e to the qii epsilon. Now I'm going to integrate over the conditional PDF for tau over its entire space. Its space is 0 to epsilon in this conditional land. Then I get the expected value. So I'm going to plug in tau equals s. And at the very end here, I'm going to put on the conditional PDF for tau, given that tau is less than or equal to epsilon of s ds, because I've already used the t in this problem. And now I'm going to go through this entire thing and put in s's for the taus. What do I know about these terms? This PDF on the end was that conditional exponential PDF, and it looked like this is the PDF, not the CDF. I was about to write down the conditional CDF. So this is negative qii e to the positive qiis, and then dividing out the area under that curve between 0 and epsilon, which is 1 minus e to the qii epsilon. Thank goodness we have found some cancellation. What else do we know? For this first integral here, we are integrating a constant with respect to t. So we do know that this is just s times f of I. And because we're in this conditional land where the first event has happened, but not the second event, the process is constant there as well, but I don't know what it is. It's some constant, and it will depend on where we moved, going from I to some j. So this is actually the next random variable I'm going to condition on. The probability, excuse the poor notation, that the chain goes from I to j when it moves. This is supposed to be the ratio of the rate. So this is qij over the negative of qii, the negative qii being positive. So I know this is a little messy of me to do it this way, but I really don't want to rewrite the whole line again. So when I write the next line, this is going to disappear and cancel with this. And the next line is, I'm going to condition on where the first move, this isn't a good sentence, went to. So I started at I, and where did I go? I go to some j that's actually not equal to I, because in this continuous time process, it's not considered a move to stay at I. So I'm going to, cancel these, and I'm going to start with a sum over all the j's not equal to I. And at the very end of this calculation, I am going to be multiplying by this probability. So at the very end of this line, I'm going to have this ratio, and I'm not going to write the denominator because it's going to cancel. So I get just qij left over here. And now let me write the rest of the integrand. This is the integral 0 to epsilon, the expected value of s times f of I. Now again, we know that the time of the second move has not yet happened in this range. And since we conditioned on the fact that we've moved to j, this is now a constant. And that makes this, down in this conditional setting, it makes it f of j, which is constant over with respect to this integral. And that means that we get the integral is epsilon minus s f of j. Now I need to take care of, I need another color. I need to take care of this. The time between events are exponential, but at the beginning of this problem, or the beginning of part C, I can't tell you the distribution of tau prime because I don't know what the rate is, because the rate of those exponentials depends on where you are. So if you're at state I, the time of the next move is exponential with rate negative qii. And I don't know where we moved to, but I do now because we are summing over where we moved to. And so I know that in this case, tau prime is exponential with rate negative qjj. And that means that I can write the blue circled probability as a tail probability for this exponential. And this is going to be e to the positive qjj epsilon